So this is a talk through to accompany the worksheet for workshop 5, where we're going to, instead of looking at a time series where time is on the x-axis and then the parameter that we're interested in, the tidal height or whatever other variable that we're interested in is on the y-axis, we're going to look at how we can transform that into what's called the frequency domain. And this is a different way of representing the same data so that we can understand better what the dominant frequencies or periods of variability are within that data set. And we're going to be using what's called a Fourier transform to generate a power spectrum, which shows us how the data varies, what the amount of variability there is at each of the frequencies within the time series. So we're going to, as usual, step through these main steps and create various plots along the way. And then for task 5 to be included in your portfolio is just looking at a different tidal data set and having a look at how changing things around will change the information that you can extract for from the data. So we're going to be working with the output from workshop 4. So if I switch to MATLAB, you can see this is the end that we got to at the end of workshop 4, where we had these 3 plots. We were looking at aliasing, we had a sort of a cumulative mean of a subset of the data, and this is the kind of the original data set. 1 year of, I'm using 2012 data from Newlin, and this is the segment of data that I'm looking at. Now, you may have been sort of experimenting with different segments and different data sets. For this workshop 5, we're looking for a segment that's at least 100 days long. So you can see on this plot where I've pulled out the subset of data that I've got over 140 days of data. So I've got a good long data set. Later on, we'll be reducing the length of the data set so you can see the effect that that has on the information you can get from the frequency domain. But start with a long segment of data, 5-6 months worth. So make sure that you do have data without big gaps in it. These big gaps will mess up the shape of the spectra, make it more confusing. So do make sure that you find some data that is nice and continuous. This did have a little gap in it that we filled in, and that is fine. But if you have big gaps in the data, then that will lead to issues. So try and find a segment of data with continuous values in it. Okay, so I'm working in my workshop 4 folder, and I might rename that in future to workshop 4 and workshop 5, just to clarify things. But what I'm going to do is I'm going to start a new script which will form the basis of the commands that we're working on. So I'll do edit and then workshop 5. And this script doesn't exist, so yes, I do want to create it. And this is a script to run through workshop 5 commands. Okay, now what I'm not going to do is put a clear all at the beginning of it, because this script is going to run on the basis that we've just run the workshop 4 script. And so you can see in my workspace I've got the original data, but I've also got the segment of data that I've pulled out, which is the T and the H, and then we've got the other things that we calculated as part of workshop 4. So I want to keep this workspace. I don't want to clear it, but what I do want to do is just to close all the plots so that we start again with our plotting. So what I now want to do is just create a new plot, just to double check, sanity check, that my segment of data is what I expect it to be. So I'm looking at the time and the height, and then I am labeling it just out of habit. So that's the height in meters for the Y label, and the X label is the time in days. So if I save that, go back to my command window and run it by running workshop 5, then I should close all the other figure windows, and then I just get this as my first plot coming out. And I can check that it looks okay. There are no big gaps in the data. You can see the little glitch here that has been filled in. That's fine for what I want, and it's more than 100 days worth of data. So this is a good data set to be working with. Okay, now what we want to do with this data, so we've got the time and then we've got the height, is we want to calculate the Fourier transform of that data. So if you look at the instructions, so we've plotted up the data set, and we want to then transform it into the frequency domain. And if you refer back to the lecture notes, the way that we can then represent this data in the frequency domain means that we'll be plotting the amount of variability, or the amount of energy, or the power at each frequency across a range of frequencies. And the range of frequencies that we can look at are determined by the properties of the data set itself. And there's a low frequency that we can look at that's determined by the overall length of the data, and that tells us also what the overall resolution is going to be. So the more data that we put in, the better resolution we have on the different frequencies that we're able to look at, and we're able to look at lower frequencies as part of that with a longer data set. And also the highest frequency that we can look at is a function of the actual sample rate. So in this raw data here, if you remember, there are data points every 15 minutes, and that means that there are 4 samples per hour, or 96 samples per day. And so the highest frequency that we can look at, which is called the Nyquist frequency, is half of that. So we would then have a Nyquist frequency in our output from the Fourier transform of 48 samples per day. So that's our Nyquist frequency. So we're going to go from a low frequency, which is associated with the length of the data, to the highest frequency we can resolve is 48 cycles per day. So that's what we would expect in our output. Now the command that we're going to use for the Fourier transform it's called a fast Fourier transform, FFT, and we'll use the MATLAB command FFT. There are different versions of this which do different things, different averaging. We're using the really basic FFT function, and we feed in the heights, and then we capture the output from that as, we'll call it FFTH equals, and then we'll do FFT. Okay, now that ran quickly. A fast Fourier transform runs even faster if the length of the data that you feed into it has a power of 2. So if you've got 16 or 32 or 64 or 128 data points, then it runs even faster. But it's able to cope with data lengths that are not a power of 2 too long. And what you'll see is that in running this command, I've created an output called FFTH, and this is given here is the same size as my input data, 14,495 data points. In my case, yours will likely be different. And it's in this complex form. Now, a complex number, if I have a look at, say, just one of those values, so if I do FFTH, and then we'll say have a look at the 100th value, then I get this output. So a complex number is made up of two parts. It's got a real part, and this is to do with the amplitude of the particular frequency that, when added together, will give the original data set. And this part here, which has got the letter I at the end of it, is an imaginary number. And the little I represents the square root of -1, which is not a possible number, so that's why it's called an imaginary number. And this part of the this number, this complex number, represents the phase or the offset in the timing of the sinusoid at that particular frequency. So you could change the overall shape of the time series by offsetting, by changing this this phase. You could change the shape of the time series at different frequencies by adjusting these amplitudes. Now, for this exercise, we're interested in this amplitude. So this is basically saying how big, at any particular frequency, how big is the signal. And so we're interested in comparing these values. Is there a lot of variability at that particular frequency, or is there not much variability at that particular frequency? Now, to actually turn this into a value that we can compare, we need to do some scaling of the output. So we can't just use this raw output, this amplitude, because it's also a function of the length of the data series that I've fed in, and also the sampling rate. So we need to do some scaling of this. So I'm going to write a function which is going to calculate what's called the power spectral density, or PSD, and it's going to output the frequencies, and then that value of the power spectral density, depending on the input data set, also feeding in the sampling rate, how many samples per day or how many samples per second are being provided. So we're going to create a new function, so edit, and we're going to call it calc PSD for power spectral density. We're using this as a function because it's a self-contained thing. We're going to be running it on different versions of the data. It doesn't exist, so yes, we do want to create it. This is a function that's going to output two things. It's going to output the frequencies that we extract, and it's going to output the PSD, the power spectral density of the Y values. So in our case, this is going to be the tidal heights, but you can apply this function to anything. You could apply it to the amplitude of the sound that you're feeding in, or the amplitude of the temperature. So we're just going to call it Y in this case, equals, and then it's the name of the function, calc PSD, and there are two inputs to this. We've got the raw data that we're feeding in, and then we've got its sample rate, which we're going to call FS. So this is the number of samples per unit time. So in our case, this is 96 samples per day, but it could be that it's 100 samples per second, or any other sample rate. We'll then write a little note. So this is a function to calculate the power spectral density, PSDY, which is the output, at the frequencies, which is the output frequency, the input time series Y with sample rate Fs. So that tells us what each of the inputs and outputs are. Now, the first thing we need to do is to measure the length of the time series that we're putting in. And so we'll call that n equals the length of the time series. And we use this shortly to apply scaling to the output from the FFT function. So if you've got a longer time series, then you get a different size of output to the a shorter time series. So we need to scale it by the length. We then need to do just what we've done. We need to calculate the Fourier transform of the Y data. I'm going to call that output big Y FFT equals FFT of the input Y data. So I'll add some notes. This is find length of time series. This is calculate Fourier transform. So once we've calculated the Fourier transform, we then need to do the scaling so that we can then compare the output when we put in different versions of the time series, whether we subsample it or whether we shorten it. We need to scale it properly. And to do that, we're going to calculate the power rather than just the amplitude. So the power, if you like, the amount of energy transferred by a wave is proportional to the square of the amplitude. So the power, and we'll call that P, is equal to the amplitude is the real part of that complex number, which is the output of YFFT. And we get the real component in MATLAB by saying abs of YFFT. That contains the real component. So we're not looking at the imaginary component which contains the phase information. We're only interested in the amplitude. We're then converting that into a power, and we convert it into a power by squaring it. And then we scale it according to the length of the data series. So we then need to divide that by n, which is the number of data points that we've got. So that sort of scales the data that we have. Okay, so if we just save that for now and go back to the command window, let's just have a look at what this the output of the Fourier transform looks like. So if I say P equals, and I'm going to take the abs of the FFTH, which is the what I've calculated up here. This is just an example that I'm working through. And if we were to square that, and then we were to divide it by the length of the data that we were using, that's essentially what our function is going to be doing. What I can then do is I can close all, and then I can do a new figure and plot the spectrum. So if I do plot P, then what you end up with is this plot. Now, what you can see is on the x-axis, this goes from 0 here to almost 15,000 in my case, which is the length of the data series. And what these are actually it's the different frequencies that we're now able to extract from that series. And on the y-axis is the power, and you can see that it goes from 0 and then it goes up to 15 times 10 to the 4, so it goes up to 150,000 in this case. And you can see that most of the values are very small, but you've got the occasional spike or big value. And to bring those out more clearly, we want to change the scaling of this y-axis. We want to basically set on this axis the y scale to be logarithmic. And what that does is it basically compresses the y-axis so that we've now got powers of 10 rather than a linear scale. So a logarithmic scale enables you to show both small numbers, so you can see many of the numbers here are down at sort of the 10 to the minus 4 level, and some of the numbers are up here at 10 to the power of 4, so it enables you to show a much, much wider range of values. So we've got frequencies along the x-axis, and then we've got this power on the y-axis. And by showing that on a logarithmic scale, you can see the details here. So you've got some spikes here that come down, then it flattens out, and then it goes back up on this side. And what you've actually got is a symmetrical distribution. And what you've actually got here is the center here is the high frequency, and then you're going to low frequencies either side of that. So we only need to look at one half of this process, one half of the spectrum, this output. So we can look from this part here through to the middle, but because it has a second half which is identical to it, we need to basically pull out this segment of the data and then multiply it by 2 to correctly scale it. So if we switch back to our function, what we're going to do now, so this is convert amplitude to power, and the next thing we're going to do is to just extract 1/2 of spectrum and scale it. So we're going to say P, which is our power, equals P, and we're going to take the first element through to the size divided by 2 plus 1. So that basically goes from the left-hand side of that plot through to the middle. And then we're going to multiply those values by 2. The most left-hand value, which is called the 0 frequency, isn't repeated, so we don't multiply it by 2. And similarly, the value at the Nyquist frequency, which is in the center of that plot, is not repeated, so again we don't multiply that by 2 for our scaling. So we say P of 2 to n minus 1, so we're avoiding the two n's, equals P 2 to n minus 1, and then we multiply just those values by 2. So that's our power spectrum. Now, the next thing that we need to do in our scaling is to calculate the power per unit frequency. So this is where the sample rate comes in, this Fs. So we basically calculate the PSDY, this is the power spectral density, which is the power per unit frequency, is equal to the power divided by the sampling rate, Fs. So that's the first of our outputs here. And then the second thing we need to do is to calculate the frequencies. So what are the frequencies? What's the x-axis going to be? And the frequencies go from 0, and they step at our sampling rate, Fs, divided by the number of points that we've got, all the way up to the Nyquist frequency, which is the sampling rate divided by 2. And that's our output. So if I now save that, and we go to workshop 5, what we'll do is we'll run that code, and we'll then produce a plot of the output. So we're going to run that code, which is the frequency, and then the PSD of the heights that we're feeding in equals calc PSD. We're going to feed the heights in, and then our sampling rate is the number of samples per day, which is 96, which is 4 samples per hour times 24 hours. So that we're going to run our function, and we'll then produce a plot, figure 2, and we're going to plot the output frequency and the PSDH, the power spectral density of the height, and we'll add a label for the x-axis, which is the frequency, and the units of that are per day. So what's the frequency in units of per day? How many cycles per day are there? And the y label is now our power density. And the units of that is the square of the amplitude, and the amplitude is the size of the variation. We're dealing with heights, and it's the square of that, so it's the meters squared, and then it's per frequency, so it's per, and then it's day to the -1. And we want to repeat that process of setting the y scale to being logarithmic, so that we can see both big values and small values. Okay, so if we save that, if we go back to the command window and we run workshop 5, we now have this output. So we've got our input time series, and our output is now the power density spectrum of the input data. And you can see that the frequencies run from the lowest frequency, or 0 cycles per day, all the way up to the Nyquist frequency. And we were expecting the Nyquist frequency to be half the sampling rate. So sampling rate is 96 samples per day, so the Nyquist frequency is 48 samples per day, and we can see that that's the case here. So what are you actually looking at when you look at this spectrum? What you're seeing are, you've got these spikes, and these spikes go up quite a lot from this sort of general curve, and the curve sort of flattens off. So down here you're seeing low frequencies, and up here you're seeing high frequencies. So here you're seeing variations that don't happen that often per day, and here you're seeing variations that happen a lot per day. And you can see that the amount of energy, the amount of variation that happen a lot per day is very low. You've got very low values here, 10 to the -6. And the variations that happen fewer times per day have then got these higher values. So these spikes are associated with the particular frequencies of the variations in the sea surface height, which are driven by the tides. Now the tides are driven by different factors. They're driven by the movement of the sun and the Earth and the Moon system, or relative to each other, and that leads to the changing tidal patterns. So we've got 2 tides per day in this location, and then we've got springs and neaps, back to springs, down to neaps, because of the relative positioning of the sun and the moon. And that's shown as these spikes here. So what you have are different frequencies which represent the different components of the Earth-Moon system interacting with each other, giving these inputs into this signal. So by looking at the exact timing of these spikes, we can then, and the relative size of them, we can start to say, well, which is the most important factor? Is it the moon in this location? Is it the sun in this location? Is it, are there other features that are important? So you can see that out of this entire range of data, we go up to a Nyquist frequency of 48 cycles per day. It's only these spikes which maybe go up to sort of 14 cycles per day, which are standing up above this baseline. So we need to kind of zoom in on this plot just to have a closer look of it. So I can set the X limits so that I get a closer view here. So we'll go back to our script, and we'll set GCA and then X lim 0 and we'll say 15 for this process. But that's something we need to start off by having a look at the whole spectrum and then seeing where the particular features are. So if we go back now to command window, do workshop 5, we get a much closer view of the just this sort of lower frequency component of the data, and you can start to see more detail here. So here you can see that there are actually double spikes. So you've got a spike here, and then you've got a spike next to it, very close by, and then you've got some spikes here, and you've got some spikes here, and there's also spikes here. And the values here are associated with the different tidal harmonics, they're called, or different tidal frequencies that are well defined, well known, because of the sort of the behavior of the Earth-Moon system is very well defined. And what we want to do is just check that they line up with the particular frequencies that are known. So given in this document, we've got a list of the periods of the main tidal frequencies. So the main semi-diurnal tide generated by the moon is called the M2 component, and it's got a period of 12.42 hours. And that tends to dominate in northwest European waters. And it combines with the S2 component, which is the solar semi-diurnal tide, which has got a period of 12 hours. When you're in shallow water, you can sometimes have higher frequencies or shorter periods. So the M4 component might become important. And in other locations, often in the Pacific, then these are diurnal components. The K1 and the O1 are associated with the tilt of the Earth on its axis, leading to different sizes of tides each day. And they've got these called diurnal frequencies, and they've got periods of about 24 hours. So what we're going to do is just on our plot, we're going to add some vertical lines at each of these periods, or each of these frequencies. So if I go back to my script, we're going to add in a line for the M4 component, and its frequency is 24 hours divided by the 6.21 hours, which is given in this table. So 6.21 hours is the period. So the frequency, or the number of cycles per day, is 24 hours divided by that period. That's the M4 constituent. We can then have the S2 constituent equals 24 divided by 12. So the solar tide, there are 2 solar tides per day, so its frequency is 2. The M2 is equal to 24 divided by 12.42 hours. The K1 is equal to 24 divided by 23.93. So that's this number here. And the O1 is equal to 25.82, 24 divided by 25.82. And we can then add a vertical line associated with each of those, so that we know where those dominant tidal frequencies are. And we can then see, okay, well, which of the frequencies in our time series are tidal, and perhaps there are some which aren't tidal. So as before with a vertical line, I can use the command xline, and then I can put M4 in more recent versions of MATLAB. In older versions of MATLAB, but it also works in newer ones, we can do a plot, but I'm going to have to add up here. I'll have to add hold on to my plot, and then we'll do a plot of the M4 on the X values, and then the Y values are just from the limits, so it's get GCA and then YLim. So that goes from the bottom of the plot to the top of the plot, and then we'll put in a red dashed line for the M4. And now that I've got that typed in, I can copy that, I can paste it. Two more times, so I've got 5, and then I can just edit these. So I can say S2, S2, I can then say M2, M2, I can then say K1, K1, and O1, O1. Okay, so let's see what the result is of that. So I'll rerun my script, workshop 5 script, and here we can see we've got our spectrum, and these red lines that we've now put in fall exactly on the peaks that we've got in our data. So I can zoom in on this plot. Let's have a very close look at these, and you can see that the highest peak here is associated with the M2 tide, and then there's a smaller peak which is associated with the S2. There's actually a relatively big peak associated with the M4, and that's because particularly around the south coast of the UK, the M4 and then this peak next to it will be the, so this is a slightly higher frequency, will be the S4 constituent, become more significant in the shallow waters around the English Channel. And these are the lower frequencies. So these are the K1, the O1, these are the diurnal frequencies. And you can see that they're slightly less, they're lower in value than the M4, the shallow water frequencies. The dominant one is the M2 and then the S2 afterwards. Okay, so we've got a nice clear tidal signal, but there are some other peaks in here, and it could be that those would be what you were interested in analysing later on. You can see there are these repeating peaks at higher frequencies. This will be to do with the M6 and perhaps the M8 cycles. So as you go into shallower water, then you will find that these peaks become even bigger. Okay, so that's the basic part of the analysis. It's starting to learn how to look at a spectrum and then pull out information from it. And it might be helpful to add some labels to these lines or change their colours and then add a legend. So going back to our worksheet, the next step is to see what differences are made if we look at a shorter segment of data. What does that actually mean? And then if we reduce the sampling rate, what does that do to the overall spectrum? So the first thing we'll do is we'll look at a shorter segment. So if I go to my script, what we'll do is we'll take all of this code where we're calculating the PSD and then we're feeding it into a plot. I'm going to copy that and then I'm going to paste it. I'll add a little note to say now reduce the length of the data series. Now to reduce the length, I can just feed in a subset of the data. So I can say here that I want to go from the first value, and there are 96 values per day. So if I want to include maybe 14 days worth, 2 weeks worth, then I can say 14 times 96. So that means that I've got 2 weeks worth of data. If I wanted 1 month, then I could put in 30 times 96. Let's stick with 14 for now. And then I want to open a new figure window, figure 3, and then all of the other things stay the same. So if I save that and then go back to my command window, rerun workshop 5, now you can see that what we've got is a change to how the spectrum actually looks. So it would be helpful if I add some titles to this so we can see what's going on. So figure 2 will add a title which is the original, and then figure 3 we can add a title which is the reduced length. Okay, so hopefully that's a bit more clear. So we've got our original spectrum. You can see there's very fine detail here, so you can see all these little spikes, and you can, if I zoom in on where the M2 and S2 are, you can actually see that there's 2 separate spikes there that line up with these 2 red lines. Now that I've only got a 2-week data series, if I now zoom in on this area, you can see that I can't actually resolve those peaks anymore. So this is the same area that I'm looking at in both plots. So with the original data series, I've got all of this detail, and I can distinguish the 2 different frequencies of the M2 and the S2, which are quite close together with the semi-diurnal tide. But now that I've fed in less data to the Fourier transform, a much shorter period of time, it means I don't have the same resolution. And if you remember in the lecture, the resolution that you get is proportional to the length of the data series. So the longer the length of the data, the more resolution that you get in your spectral output. And this makes sense. If you want to resolve the difference between two frequencies which are close to each other, you need a long enough series of data for them to move in and out of phase with each other. So we need to capture at least a spring leap cycle to separate out these 2 frequencies. So what length of data do you think you need to well resolve 2 closely spaced frequencies? You could feed in different lengths of data, maybe try a month's worth of data. Can you then start to resolve two spikes here in this region around the M2 and the S2? And the final part of the exercise is to reduce the sampling rate. So what we're going to do is to use the script that we, so now what we're going to do is use the function that we created in the previous workshop, where we created a subsample, and we're going to subsample the data. So I'm going to copy this final chunk and then paste it again. So we're now going to reduce the sampling rate of the data series. So now we're going to create a subset of the data. So we're going to reduce the sampling rate to maybe 1 sample every 4 hours, rather than sort of 4 samples per hour. So we're going to create a subset of the time, and then a subset of the heights, and then we're going to use our subsample data function from last time, where we feed in the time and the height, and we're going to take every 16th data point. So that's basically sample every 4 hours in this case. And we can then, instead of feeding the raw heights in, we can then feed our subsampled heights in, and the sample rate is now 6 samples per day. So if we've got every 16th data point, which is 1 sample every 4 hours, that means that we've got 6 samples per day, which is our sampling frequency in our spectrum. And then we can produce another plot. So this is now going to be figure 4, and we're going to show, and this is now a reduced sampling frequency. Now, having a think about this plot, what it will be doing is impacting on what the highest frequency is. So if we have a sample point every 4 hours now, that means that our Nyquist frequency will be 1 sample every 8 hours, which means that it's 3 samples per day, 3 cycles per day. So our X limit line we need to remove, and I'll also remove it from our first plot where we've got our original. So we'll just comment that line out so that we can then compare. So I'll go back and then we can compare the output. So workshop 5, what we can see is we've got our original spectrum here, and the Nyquist frequency goes all the way up to 48 cycles per day. And then we've got our reduced sampling frequency, and in this case the Nyquist frequency is only going up to 3 samples per day. So we've got a much reduced spectrum here, and in fact we no longer are able to resolve these higher frequency components. These are the M4 components that we can see are contained within the spectrum and are important. And by only having a look at a subset of the data, we're not able to see those anymore. We are able to see those lower frequencies. We can still pick out the M2, the S2, the K1, the O1, but we're not able to see the M4 anymore. So by only sampling at a lower frequency, we're not able to see higher frequencies, and that's shown in the spectrum that's then cut off. Now, looking at spectra is a new thing. It's quite a different way of looking at data, but it does enable you to pick out what the dominant features are in data. You could apply exactly this technique to looking at maybe sound that's been recorded in the ocean. And you could then look at the frequencies and the power spectral density as a function of frequency, and then use that to identify what animals might be living in the water. So to identify different cetaceans, you would look at the spectrum of the sound, and then particular frequencies are associated with particular species. So it could be that if you're looking at orca, they have a different spectral characteristic to if you're looking at common dolphins, for example. So the follow-up for this work is basically just to repeat this process but using a different data set, and also to sort of experiment. So what length of time series do you need to resolve all of the features that are important? What sampling frequency do you need to resolve the range of frequencies that are included? So try and vary those two things within these data sets, so you start to get a feeling for how the detail and the information that you capture within a spectrum is impacted by the length of the data and also the sampling rate.